I'm building infinite reasoning LLM that can have infinite context window, or maybe trillion tokens context window. It's same in this case. In this video you can find my LLM just 250 lines of code, and in the latest video we designed experiments and research. I'm running the experiments right now. I'm training it. It has Mamba heads and attention heads. Mamba heads are linear and attention heads are quadratic scaling. So first I'm gonna test all of these configurations. Only Mamba heads, only attention heads, and then Mamba attention, and then attention Mamba. And then after each there is a feed-forward network. In between each, after each there is feed-forward network. And right now I just wanna test for just 3000 steps if it's saving properly, if it's training, if validation loss is going down, and all of this stuff. This is like a test run. Model has around 50 million parameters. If you want to learn more about how Mamba works, check out this Mamba 2 video, or check out my Qwen 3 from scratch and Llama 4 from scratch if you want to learn about attention and LLMs in general. The first one trained all Mamba heads. It failed to upload Hugging Face. I'm gonna fix this bug. I don't know what's happening. So for this one we can check validation perplexity is not going down. Validation loss is not going down, which is not good. Training loss is going down, but in the previous video validation loss and perplexity were exploding. At least they're not exploding anymore, but I don't know why they're not going down. So maybe it's this particular setup. All Mamba, let's check all attention heads. Actually it's going down now, so maybe this is good. Validation perplexity going down. Let's see. Validation loss not going down so much though. Validation loss here is 6, so I think it went down from around 10, so that's good, but it didn't go down enough. I don't know what we are evaluating on. Validation loss should be same as training loss though. Sometimes our training is very fast, so 3000 steps, just 3 minutes. Here it's 2 minutes even. And then all Mamba heads, it's 5.5 minutes. So all attention heads 2 minutes, all Mamba heads 5.5 minutes. That's because attention is more parallelizable, I believe. If we look at GPU utilization, 100% almost. I like these. So validation perplexity is just, it's not going down. I need to figure this out. Validation loss isn't, like, I have all of these experiments and it just ain't. So now all attention, why is it actually worst? I expected all attention to be like best. I don't know, I need to see the architecture again. So all of it finished, the 6 or 5 experiments, and then I told it, write a report in a markdown file. But I hope it doesn't, okay, experiment is gonna create a new markdown file. Let's see. How does it know my university? What? So it wrote a bunch of stuff. How do different layer patterns or arrangements affect model performance? We got Mamba, we got attention. So 24 to 26 million parameters varying by pattern. 3000 training steps, which is just a few minutes. Sequence length 512, batch size 8, these could be higher. We are using just 35% of GPU's memory, so I guess if we increase batch size, we will just use more memory, which is gonna train better, or faster, I should say. We got these 2 architectures, these 5 architectures. So let's see the results. Attention all is smallest, Mamba all is largest. Final validation loss, attention smallest, as I expected. I don't know if attention has to be smaller than Mamba, but it's just what I experienced. 1, 2, 3, 4, 5, 6, 7, 8, okay. But the difference, there is a little bit of difference. I wonder if I ran this whole thing again, would I get like same loss? I think I would. Final perplexity, but I should also tell it to track training perplexity as well. Just so I can see difference between training and validation, because I don't know if validation, why is validation so different than training? So all Mamba heads also takes most memory here. And it's slowest, look how slow it is. Look how fast this is, all attention, look how fast, 500,000 tokens per second. This is only 200,000. I don't know if this can go faster. Maybe it can, I'm not sure. We'll see all of this, we'll figure it out. All models show consistent learning patterns. Rapid initial loss reduction in first 500 steps, gradual improvement from 500 to 1500, stabilization in final 1500, no significant overfitting observed. How is there no significant? Because training loss is a lot lower than validation loss, as I understand. Validation loss just ain't going down. It's not going down. So it seems like this blocked pattern, where we just have two blocks, performs worse than these alternating patterns. But we need to test more on that. Now I'm gonna use GPT-5, and it's actually quite good. And I'm gonna tell it to figure out why validation loss is not going down during the training. But this could actually just be because we are training on too little data. And you see here, we are measuring first at 500 steps. So from here, what are these like spikes and valleys and dips? Are they different, how do you say, documents maybe? But it's still going down from this point. So it should also go down in validation loss, but it's not. Okay, validation perplexity going down, finally. I think, yeah, it's going down, that's it. Okay, so I think the problem was the model was, we had too big dropout, we'll see. I just copied entire code into this guy, Cloud Opus, and then it generated this whole, and this is what it did. Increase learning rate from this to this, reduce dropout because it was too big, 0.2 is too big. Added learning rate warm-up for stable training start. Increase dataset size to 5,000 documents. But I still train it on a lot less than this, I think. But it was going down. It was just for testing for me. Improved SSM layer with better numerical stability. What did it do here? It added gradient accumulation for more stable updates. Yeah, we also fixed the loss calculation because it was not calculating properly. And then just evaluate with more batches. Now it says it should plateau around 4.5 to 5 and perplexity around 90 to 100, which is reasonable for this model size. So we got perplexity around 170, 180, okay. And then we got this guy around 5. So Opus actually predicted quite well. Now the model is just too small, and that's it. Yo, why is my training loss 170? What's happening here? Validation loss 5. Maybe this is not calculated properly. But look how smoothly it's going down. I think it now works. I deleted some of the files, moved them to this folder. I'm gonna maybe delete later. And now I'm just running the training again. Why is it saving models so often? But validation loss is going down. I'm just trying it to see what it looks like right now. I think everything is going down properly. Training loss and validation loss are maybe more similar. You see, training loss 4.8, validation loss 5.3. So they are very similar now. We are now achieving better loss and perplexity than other runs. Now it's best. So there was no bug. It was just not good like setup before. So now it's a bit better. Now let's ask Opus what it wants to do next. There is this extension in VS Code. It's this one. It lets you copy entire folders content, like right click and copy content. And you can paste it into Opus entire code. It's not too big. My code base here is very small, a few files. And now I asked it, which experiments do you want to run? Just write it in this experiment, run experiments sh. Let's see what we got in the next experiment setup. We're gonna make directory experiments and logs. Steps 10,000 for each, that's a lot. So this will just log which current experiment we're doing. Baseline architecture. So after these two baselines, we go with two alternating, and then double alternating, and then some structured, so this sandwich, this thick sandwich, and then groups. Why don't we have Mamba sandwiches? Groups. We got Fibonacci, 9 layers. I just need to check because this guy doesn't know how to count letters. So I don't know if this is 9. I need to check manually all of these. So then we can scale testing in phase 5. So I'm going to comment that for now. I just need to check the letters here. I think I'm just going to say bash and run experiments and start. Let's see how it goes. What? I have to first check each for 300 steps though. No way I can do 10,000 and then this run analysis script doesn't work or something. A few updates. I made tokenizer and data shared. I also tested on 300 steps and it looks like it worked fine. I'm gonna show you results. So here it's tokenizing. I got this shared data file somewhere and then it's gonna tokenize it all and use. So I'm gonna run on now 10,000 steps. It's gonna be 27 million training tokens. Still, we wanna train on 1 billion tokens if we wanna have a good training run. But 27 million is okay for this small scale experimentation. For each experiment, 27 million. And you see our model size is around 27 million and data should be 20 times bigger than model size. So we should train around 1 billion or a bit less, but 1 billion is also good in order to actually fit the model properly. And we can even go more than 1 billion, 2-3 billion, there are maybe methods. So you see validation loss is going down slowly. Perplexity also going a lot down. I really like this. I think this is going very well. I just don't like this logging in this console. What is this? It is what it is. The results of the 300 step run are surprising, although it's actually very small run. So we are not sure this is how it's gonna be in the long run. But this sandwich actually works the best with attention around. I know that NVIDIA is using just one attention head. So maybe that's similar like this. And you see this pure attention is actually worst. But I think this will change. This can actually be even best if we just train for longer. So I think we cannot actually look at this. This is just 300 steps test. But my loss, my graphs, my charts, everything is going down. It looks so nice. Memory. Oh, I think we're underutilizing memory again, by the way. Just 26%. I forgot to increase memory, but it's okay. Just let it run this way. So I want to fix this logging and I want to increase my batch size because memory is underutilized. I want to double it. So I need to actually change learning rate a little bit, increase it a little bit. And warm-up steps and gradient accumulation goes back to 1. So it's just going to train faster. It's going to do same thing as 16.2, but it's just going to train faster and use more memory at 32.1. Our statistics are going down so nicely. Perplexity going to 50. That's good perplexity, bro. That's good. This is around 4. Validation loss. And then training loss. We just need like 20 times more data than this, but this is also good. Looks like currently our runs look good. We are running for 10,000 steps. It's just 3 finished though. We're gonna need to wait like a few more hours. No, it's just around 12 minutes, so maybe 1 hour. 12 minutes per experiment, around that. And everything is going down, 3.7 and 3.7. Training and validation loss seems pretty similar. If I use age 100s, I'm gonna pay $14 per hour. I'm gonna need a bit more funding here, but that's for scaling a lot. Age 200s, they give even more memory, but this is just for big models, but I think I can fit here huge models, like 30 billion parameters or 50 or 70 even, if I split it amongst 2 age 200s. But this is not for now, this is for later. Right now we can just stick to 8 times this if we want to distribute, but maybe we can just run separate experiment on each one. And if I go here on demand billing on Novita, spot billing actually has age 200s and age 100s at 50% off. I did not know about this. We can use H2. I can start using this actually then. This is crazy. So right now I'm using this one at just 18 cents per hour. So if I use 8, 144 per hour, still very little money. Very few dollars, I guess. So 8 of these, I think we need to submit a, no, $13 per hour. This is so cheap. I need to use this, bro. I'm gonna start using this. That's crazy. That's crazy. Let's go. Let's go. Let's go. Let's go. Let's go. Let's go. We can train now. We can train better. This will make our scaling experiments a lot cheaper then, and we can do them a lot more of them. So I asked Claude Opus what I should use, and for this model it recommends just staying at 4090 because it's a sub 500 million parameter model. We just have 30 million parameters. 10 to 50 million. It fits easily on 4090. You see, it thinks it's 50 cents per $1 per hour, but it's actually just 19 cents. It's less than 20 cents per hour if you go spot billing. So it says here 4090 doesn't have NVLink for fast communication between GPUs if we split the model onto multiple GPUs or data, but we don't need it for a small model like this. It says, I think we will just use simple data parallel on 4090s for this GPU, so we will just have a copy on every GPU and the data going everywhere, and then gradients just adding up in the beginning, at the end I should say, and then getting the latest gradients update to every model, and then continuing to every copy of the model after they all add up and average. But it seems like at 10,000 steps we get distinction between different architectures. So some converge a lot lower. It's very surprising that there is no too much difference between attention heads, Mamba heads, or some mixings. I watched some YouTube video that says for vision models that those models that are good are all good in the same way, but those that are bad, every is bad in its different way, every fails in some different way. So maybe it's same for language models. If we build them good, there is like some way to build them good. And then that's why they're all like same, very similar here. And it looks like their performance is determined by the parameter count, not by Mamba or attention architecture, which influences the model only a little bit. Maybe there is some common thing that we built in both Mamba and attention that makes it learn. So maybe we need to discover that. And then I asked if it's better to split experiments on 8x 4090 or run 8 independent experiments, one of each GPU, or use 8 for every experiment and then go sequentially. And Opus says, looking at your code, running each experiment on a separate 4090 is likely better for your case. Here's why. Yeah, it's easier debugging because I have just 4 separate scripts and independent experiments and setup. And you see here, every experiment is 10,000 steps. It's running for like 14 minutes. Maybe I can just let it run 1 hour on each 4090. This is something to consider. If I go data parallel with 8 times 4090, effective batch size becomes 256. So I need to scale learning rate by 8. But this might hurt convergence for smaller models. More warm-up steps needed. So I guess without complicating, just run each one on different GPU, yeah. And what's even funnier, it seems like I can just create a script and load 8 GPUs into a single machine and then just run each experiment on a different GPU without loading 8 different machines or instances. Here, result is launcher.run parallel max GPUs 8. Now while we are waiting, let's learn more about our architecture and LLM. Experiment config. So this is how we draw the heads. We select Mamba, Mamba, attention, Mamba, attention. So we need to try the Mamba attention and then all Mamba. This is how they had it in Nemotron, Nano Nemotron, NVIDIA. Then we have improved SSM. So this should be called Mamba. I don't know why it's calling improved SSM, state space model. So the improved SSM adds numerical stability through clamping values to prevent overflow, underflow. we are clumping it here, which we should be doing. Using soft plus activation for smooth positive values and layer normalization for stable gradients. Here we see soft plus. So it seems same as ReLU, but just around here where it's most important, because around 0, our weights numbers in neural network are always going to be around 0, -1, +1. So it gives smooth approximation of ReLU. So maybe this is better when neural network, is using these activation functions to separate some data points. There is a smooth line here, so it can maybe separate a bit better. And if it's using 2 of them, then it can make like 2 smooth these, but instead of ReLU, which is like sharp. So I guess maybe it's better. I would guess it's better. Maybe we're gonna test this, but then we would be testing a billion different things. So maybe we're not gonna test it. I'm gonna ask you to explain this softmax and delta better and why we have minus here. Then we have data loader with shared manager. It's gonna cache token data for every experiment and just reuse it. This model is hybrid model config to GPU. And for layers, it's gonna generate these layers. If it's M, it's gonna use improved SSM. Here we have our simple attention. You just query key value. So here, if it's M, it's gonna initialize what I already said, but if it's otherwise, just simple attention layer. Then we got learning rate scheduling. This is what improved our validation loss and perplexity to go down. So optimizer, number warm-up steps, number training steps. I think we want to use mu on optimizer here, by the way. I'm going to try to find best architecture, and then I'm going to try to use mu on optimizer there and compare it with Adam W. Here we have mixed precision training, CUDA. It's going to automatically convert to different precision by using this scale and passing loss. I think I was looking if there are any bugs, but I don't see any bugs or issues here. Maybe we need to understand how Mamba heads work better, because that's a bit difficult for me to understand, because I just started understanding it yesterday for the first time. But given that I understand attention and neural networks, I think it will not be so difficult. Gradient accumulation, I think we're not going to use this one. We just increase batch size. Accumulates gradients over multiple forward passes. Updates weights only after n accumulation steps. Enables training with limited GPU memory. But if I fill my memory, should I still use gradient accumulation? How should I decide that? I'm not sure. Then we have metrics tracking, evaluation with proper masking, early stopping if perplexity doesn't increase, I think. If best validation loss value doesn't increase for 3 times, then we early stop. I just want to understand Mamba heads a bit better. So soft plus and Y, we have negative in calculation of A. We already saw that soft plus is a smooth approximation of the ReLU function. So log of 1 plus exponential of x. Who came up with these? How do you come up with this? I guess you try a bunch of stuff, or maybe some mathematician who has intuition. We can see some example values for soft plus. So soft plus of -10 is almost 0. We saw it going very close to 0. -5 is very small. Now -1, 0.3. It's a bit on the y-axis up there. Here, it's a bit on y-axis for -1. Then 0, it's 0.6 on y, which is not nothing. It's actually quite good. It's a big value. 1.3 for 1, and then it starts to go up. But our neural network is gonna be in this range, so we're gonna get these numbers around this. So what is delta in SSM context? Delta represents the discretization time step in the SSM. Delta is a learnable discretization parameter that controls how fast or slow the SSM state evolves. It's computed per token per channel, not related to sequence length. So it controls how much of the previous state is retained in the new state. So if it's small, then a lot of state is retained, but if it's big, then only a bit of previous state is retained, and the new token influences the new state a lot more. When this happens, you just go here, load, you show you're not a robot, and then you can, so just go to different one. So if delta is big, then new token influences the state a lot more. Yes, exactly right. Large delta, new token dominates. So we have our A, which is a vector. I explained it in Mamba 2 from scratch. Mamba 2 explains step by step in this playlist below. It also controls how much of the previous state is retained in the new state. So we multiply A with delta, and A is negative. So larger delta is equal to smaller decay, because we say e to this, so big negative number will give us smaller number here, or a number closer to 0. So when delta is large, decay is small, old state matters less, new token dominates. You can just think about this a bit, because big delta will make this decay very small, so we multiply old state with a small number. So the influence, so we will get just a bit of old state. I like being invisible, but I need to have my webcam. We have a lot of experiments going on here. Which one is best? Double alternate A first. Double alternate is AAMMAAMMAA. But we have 10 layers here. Why do we have 10? Okay, so it looks like alternating are best. Double alternate has 10 layers. And if you see alternate A first, it's second best, and alternate M first, so this is just AMAMAM or MAMA. And then sandwich, and then thick sandwich, and then grouped is even worse, and then baselines are worst. The more alternating, the better it seems. So this is sandwich, it just has M's and then A's around. And then thick sandwich is 2 A's around, 4 M's in. Grouped are also not so good. I think we are towards the end of the experiments. UNet style, this is similar. I think so the best ones are gonna be alternating ones. But you see how from time to time, for example, sandwich here has looks best, and thick sandwich looks best in the beginning, but later they fall off, so it's a scam. It's like McDonald's advertisement versus reality. In the beginning, alternating are not so good, and then in the beginning it looks like when we group them it's better. Except baseline, so baseline attention is actually worst all the time. And I don't even see baseline Mamba. Where is it? It's also very bad. But as we go on, alternating becomes better. Interesting finding. Why does alternating become better? We can look further into that and how that behaves. Now, is alternating using more compute and time? Maybe, but we are bottlenecked by data. There is no more data. So this is all same amount of data. So we should look at the total steps bar. Is this same amount of data? I need to confirm that. Yes, every experiment uses the exact same amount of data. By the way, I heard Cloud Code is the best thing for coding right now, not anything else. But I just bought Cursor subscription, so it is what it is. Actually, my views are going strong, and these 3 latest videos have exactly the same number of views for some reason. Maybe same people watch them. The divergences training is just quite big. Full Mamba baseline is actually not converging as good as alternating. And I have double attention 10 layers here, so that's why it has most parameters. I need to check that. I think if it had 8, it will perform worse than alternating, but we need to check that. I will end this video here. This is training for a long time, so I need to publish this video, and in the beginning of the next video I will show you full results, and then we're gonna continue with our experiments. I need to set up more GPUs as well because this is too slow, so I'll do it for the next video. Just go to the description of that video and check the playlist, or go here to playlists, and it's this playlist that I'm researching right now. Okay, then see you next time.